The very first question, what is an algorithm? Let me just write the topic. So we start by defining an algorithm. So okay, so first for motivation, this problem, what P versus NP is one of the 7 problems that can fetch you $1 million if you solve it. So it's one of the millennium price problems. Others being the Riemann hypothesis, Navier-Stokes equation. This is just one of the 8 problems that have been solved, and the other 7 are still open. So this is one of those. And in some sense, this is sort of the simplest to explain. The Riemann hypothesis being the other. Uh, so yeah, let's see. And this is sort of at the intersection of math and computer science, because it's related to theoretical computer science, which is just essentially just the maths behind computation. And yeah, we'll see. So we let's start by defining what an algorithm is. So 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 can anybody just tell me what an algorithm is? Just any rough definition would suffice.
Like a sequence of steps to find something, or
Exactly. Yes, exactly. It's like a sequence of steps to solve an instance of some problem. Of rather rules or something. Mm, To solve an instance, solve instances of a problem, or solve a problem. So it seems vague, but let's look at an example. Like, so let's look at this famous example of GCD. Sorry. So we have GCD of A and B. Let's say A and B are naturals. Yeah. What is the method to find the GCD? So we know that we divide the larger from the smaller, and then the original smaller element, I mean the smaller element and the remainder, you compute the GCD of those two, right? And then you keep doing it till one of them divides the other, in which case the divisor is the GCD. Right? So this is the famous Euclid's method or Euclid's algorithm. So how is GCD defined? So we say if A divides B, well, okay, so we need to check if A divides B. So, okay, so let R be the remainder. Okay, yeah, first, before that, we also need to see which is bigger. So let's just say A is bigger, right? So let, or at least as much. So let R be the remainder when A is divided by B, right? Now, if R is 0, we we output R, because that's the answer, right? If the remainder is 0, then the answer is, oh, sorry, output B. Because if the answer is 0, then the GCD is indeed the smaller number. Otherwise, what do? We output the GCD of B and R. So we can just say out, or rather, oh yeah, sure. Let's just say output GCD B and R. So we have this sort of procedure for GCD, right? This is an algorithm. Can you think of some other algorithm for GCD, which may not be as fast? So what we could do is we could try everything from B and go smaller, and let's look at the first number that divides both A and B. So we could also have an algorithm like this, right? GCD AB from K is equal to B. Again, I'm assuming A is at least B to K equal to 1. Check if remainder when A is divided by K is 0, and the remainder when B is divided by K is 0. If the answer is yes, so that is, if this happens, then just output K because it's the largest number that divides both of them, right? So just keep doing it from B to 1, right? So if you fail, then you reduce K by 1. So you're checking from B to 1. Just keep checking which is the first one that divides both A and B. So these are both methods to find the GCD, right? So when do we say that one of them is better than the other? So is the second method better? Is the first method better? And what do you mean by better, and why do you say it's better?
The first is better because it takes at most as many as the second.
Why? Yeah, that's a good idea. So how do we talk about how good an algorithm is, right? So what makes an algorithm good? So the main parameter is the number of steps taken to solve the problem, right? So just as an instance, suppose my input is 198. So in the second algorithm, note that I will check everything from 98 so on to 2, right? So that takes a lot of time, right? So here I will check 98, 97, 96, 95, so on. What about here? Here, I just have GCD 198, and my first step would be to just find the remainder when 100 is divided by 98, which is 2, right? So once I have R is equal to 2, I will go into this branch, which is to find GCD 98 2. And then my remainder will be 0, and I'm here, so I'll output 2. So it barely took any time compared to the second, right? But what guarantees that the first algorithm is always sort of fast and the second? Well, okay, it's easy to show that the second may not be fast, right? For example, if I take A and A minus 1, it will take me A minus 1 steps. But maybe there are other instances where the second algorithm does as good as the first, maybe for small instances, but we don't really care for small instances. The main difficulty in algorithms is to find GCD of larger numbers, right? So what can we say about this? So by the way, when I say number of steps, I mean number of such sort of small, easy things that I can do. Sort of, for example, to find the remainder, I need to divide A by B. That's sort of easy. It's not like a one-step process, but let's say it's one step because it's easy enough. Right? Let's call it one step. And then maybe checking if R is 0 is one step. And then outputting something as one step. And then calling this and outputting as one step. Let's say something like that. So this may take like, I don't know, 8 or 9 steps, because each time GCD is called, you may need like 4 or 5 steps, right? While this takes sort of like 98 steps. In fact, it takes more because you need to check this, and then you also need to decrease K by 1 and then check. So maybe 98 into 3 or something. Right? Either way, this is much larger. Even if finding the remainder takes like 10 steps internally, even then this is like 20 something steps, and this is like 980 steps, whatever. Right? I mean, okay, what I'm trying to say is that we can think of these simple operations as one step. And so we can count how many steps this algorithm takes. So how many steps does algorithm 1 take? Well, okay, first algorithm 2 take. We can say that it's some constant times b, right? Where this constant is, if we regard these as 1 steps, then something like 2 times b, right? Not necessarily, it's more like 2 times b minus the GCD, right? Because we go all the way from b to the GCD. The number of steps would be something like this. Let's just ignore constants. And let's say there's some constant here, fixed constant, times b minus g. And this may be as almost as large as b, right? This may be this large. And even if the GCD is just half of b, even then it takes c times b by 2. I mean, if the GCD is not b, then it's at most b by 2. So if the answer is not trivial, then it will take at least these many steps. So that's not very good in some sense because b could be quite large. Let's talk about the first algorithm, right? What about A1? So what do you, so can you think about how many steps the first algorithm takes? Any upper bound is fine, you don't need to be exact. Yeah, should look better. So where A2 is the remainder when A0 is divided by A1. A3 is the remainder when A1 is divided by A2, etc. So look at this algorithm. What is crucial is how many times we keep reducing this thing. So for example, if I have 23 and 16, then I'll take some 4 or 5 steps here. Let's say 3 steps here, 3 steps. And after doing the 3 steps, I re-invoke the GCD function, but on smaller numbers. And then 3 more steps. And then I have 7 and remainder when 16 is divided by 7, which is 2. And then 3 more steps. They get 2, 2 and 1. And let's say 3 more steps. And I'm able to output the answer 1. So it took like 12 steps. So the crucial thing is how many jumps are there and just multiply that by 3, right? Or whatever constant it is. It'll be some constant every time. So given A and B, can you find some sort of a bound on the number of steps needed?
I'm not sure about a bound, but I guess it should be roughly logarithmic.
Yes, you're right. So it is roughly logarithmic in these numbers. Like for example, log 16 is 4. Coincidentally, it's exactly 4. But you are right that intuitively it feels like the numbers get like half each step or something like that, right? And so if you keep halving the numbers, then in log n steps you'll reach 1 on the GCD, right? So you are right, it will be logarithmic, but can you prove that?
I'm not sure about this proof, but let's say f of m comma n is the number of moves it takes.
Okay.
So you have f of m comma n equals f of m minus k n comma n plus k.
Uh, it's not cascade.
As long as like assuming k is assuming m minus kn is positive.
yes.
Sorry,
So,
less than n or whatever.
so this is the remainder. I'll use this symbol for the remainder. So this is true,
Sure.
right?
Yeah.
Mhm.
So so let's just say that f of m comma n only depends on the largest number.
Okay. Yeah.
So let's say g of m equals so let's say m is greater than or equal to n.
Yeah.
So you have mm, just a second.
You're trying to say that I want to bound this by some function of just m, right?
Yeah.
And then show that this g can be long, something like that.
Yeah. Okay, so let's say m equals like lambda n for some real
Okay.
lambda. So you get g of m equals like roughly c plus f g of n, right? Because we're saying it. Sorry. It only
Uh,
depends on the largest number.
yes. So by induction, sort of, I know that this is at most g of n.
Yeah,
I mean,
sure.
induction hypothesis. Yeah. Okay.
So then you get like g of lambda n minus g of n equals floor of lambda.
Uh,
Like roughly, not equal to, but
well, I mean, the problem is that what if n is m minus one, right? Then you're saying sort of if you sort of apply induction hypothesis, then you'll only be able to say that g of n plus one is at most c plus g of n, which would just give me a linear. I mean,
Mm,
sure,
right.
sure.
Some
In
of
the
these two things has to half each time. So in log 2 of n plus n steps, it has to reach 1 or less. So that gives that a bound. No, log
what
2 of n plus n is maximum of log 2 of 2m. Sorry. Yeah, where m is the maximum.
what reaches half? Sorry, could you repeat?
The sum of these two, like 23 plus 16 becomes 16 plus 7. So it has
Oh,
to half each time, right?
so your invariant is that the sum of the two numbers half becomes at most half of the previous one. So then you keep halving. Okay.
Yeah.
Is that true? Can you show that? In fact, is it?
Oh, no, that's not necessary.
It's not necessary because I could have something like
Yeah.
23 and 11 or 12, which becomes
Oh,
12
right.
and 11. And this sum is 35 while this sum is 23. But maybe what you're saying is true. Maybe not half. What even if it's like 3/4, you're done, right? Even 3/4 is enough. So you have A and B, and then you reach B and the remainder, right? So you want to sort of compare the ratio of A plus B and B plus A remainder B. So can you give an upper bound which is less than 1? Even if it's 0.9, it works. Any sort of upper bound. You can take cases on A if okay, so what if A is very large? So let's say what if A is at least 2B? Then what can we say? Wait, sorry, I need this to be more than equal to something. I need the reciprocal to be less than equal to something. Sorry. This should be less than equal to something. Yeah. So if A is at least 2B, then you can say that this is at most 2B plus B, and A% B is at most B, right? So this is 2/3. And what happens if A is less than 2B? But it's always at least B. Then what can we say? Then what even is the remainder? If A is at not even double of B, then what is the remainder? In terms of A and B, it's just A minus B, right? Is this clear?
Yeah.
This is just A, because this is just A minus B over A plus B, which is A over A plus B. And what can you say about A over A plus B? Since A is less than 2B, this is at most 2/3. That's strictly less, but it's fine. So yeah, you indeed make the sum of the two numbers 2/3 at most each step. And so after some logs, okay, so if the initial sum of the numbers initially is some n, then the next step, the sum will be at most 2/3 of n. So on after k steps, the sum will be at most this. So if this is less than equal to 1, then we would never have reached this place and we would already have found the GCD somewhere before, right? Because we would have stopped before. So when is this less than equal to 1? When 3 by 2 times k is at least n, so k is at least log base 3 by 2 of n. So if k is equal to the ceiling of this, so this is an upper bound on the number of jumps that will be required, right? Because if there existed two numbers for which these many steps are needed, not these steps, sort of these steps are needed, then at some point we would reach two numbers that are both positive integers whose sum is 1, which is a function. Maybe I need a plus minus 1 here, but it doesn't matter, right? And so whatever number of steps is needed here, 3 times this is an upper bound on the, so this n is 8 is an upper bound on the number of steps needed here. Yes, but note that A could be much larger than B, and we gave a bound only in terms of B here. So we are still not sure why this is much better. This is a good bound, by the way, but we need a better bound.
I mean, in one step, you can reduce the numbers to less than the minimum of them.
Yes,
So
exactly.
it's plus or minus 1.
Exactly. That's the point. So instead of giving such a bound, what we can say is that after the first step, let's apply this result from here on, right? Because A could be much larger than B, but I know that the remainder when A is divided by B is much smaller. I mean, it's definitely smaller than B. So instead of that, let me sort of take this as one separate thing with 3 steps and now apply this result and get 3 times ceiling of B plus A% B, which is at most 2B. Now this is definitely much smaller than some constant times B by 2, right? Because this is logarithmic in B while this is linear. So this is sort of like exponential versus, I mean, this is sort of like exponential in this. So this is why algorithm 1 is much better. Than 8. But there's more to it that I want to talk about. So sure, it is much better. But we can say something more about A1. Remember, what was the input to the algorithm? It's two numbers, A and B. So what is the size of the input? That is, by size of the input, what do I mean? I mean, how will I convey to the algorithm what A is and B is? I write A and B in their some decimal representation, right? So if I have the number, I don't know, 500,000, then I write it like this, right? So I don't need to give a number as big as 500,000. I mean, I only need to use 6 digits, right? So what matters is the number of digits I have to give. Right? And similarly, if this is some number like this, it's in the number itself is in the thousands, but the number of digits I need to provide is just 4. So the size of the input is actually log of A plus log of B with ceiling, right? Let's just say it's this, or maybe let me write this. Is it ceiling or should it be something else? Maybe it's floor plus 1. I think that's more accurate. Yeah. So this is the size of the input, right? So now notice that in the second algorithm, the number of steps taken instead of 3, let's just say it's some constant, right? Times 1 plus log 2b. And how is it related to this? Is it, I mean, if this number is n, then is this like the square of n, or is it like 2 raised to n, or does it behave like n, or does it behave like 10n, or does it behave like n square? So what is the behavior? So how is this related to the input? So that is, if I have an input, if I give you an input, how long does it take you to compute the G3 in terms of the size of the input? So how is this related to this is what I'm asking.
It's some constant times this,
Why?
because log 10 is log 3 by 2 by log 10 times
Yes.
C.
Exactly. So if, let me call this O, then what is O? O is C times 1 plus log. Okay, let me just separate out 3 by 2 and 2. So log 3 by 2, log 2 base 3 by 2 is like at most 2, definitely. So this is at most this much plus log 3 by 2b. But what is log 3 by 2b? It's log 10b over log 10 3 by 2. This is, well, some constant times 3 plus, well, definitely log 10b is less than n, right? So this is less than equal to, I'm just bounding it very crudely, and this is another constant, right? Let's say c prime. So this is some linear function in it, right? So more specifically, I care about polynomial in it. So I have this algorithm that takes some in. So let me call this polynomial f of n, or rather capital P of n. So what A1 guarantees is that if the input size is n, then the output is given in after P of n steps. And the steps is often referred to as time as well. So instead of steps, now I will call it time, because the number of steps is directly proportional to the time taken, right? So think of this algorithm being done by some sort of a computer. So you care about how much time it takes to do. And so this algorithm is what is called a polynomial time algorithm for the problem of finding GCD. So it's a polynomial time algorithm because this is polynomial. It's called polytime algorithm. And problems for which there exist polynomial time algorithms are called polynomial time solvable problems, right? So therefore, since I have an algorithm that is a polynomial time algorithm to find the GCD problem is a polynomial time solvable problem. And there are many such problems. So let me give you one more. Let's discuss 2 or 3 examples. So sorting, or rather, yeah, sure, sorting. I have a sequence of numbers. Let's say they're like cards that are flipped, right? So I have n flipped cards. Each with a number on it. Let's say it's a binary number this time, right? Or actually, let's just say it's a number. Why complicate things? Natural numbers. So the face down, right? And what you're allowed to do is pick up any face. Well, you can well, actually, I don't think I need face down, but okay, you have n. Okay, so let me just simplify the problem. You have just n numbers, and you have to sort of sort it. So they're written in this sort of manner. Let's say 4, 3, 8, 7, minus 1, minus 2. And then you want to rearrange them in a sorted order. Right? And so this is polynomial time in the input size. So first of all, it is important to know what the input size is. What is the input size here? For simplicity, let's just say that all numbers are small enough. Let's say the numbers are between -1000 and +1000. So then each number just needs 4 digits to write, 3 digits to write at most. And so the input size is at most, well, actually it's at least n and at most 3n. Let's just say it is 3n because let's just say, okay, actually I should write 4n because there's a negative sign as well. So 4n. Because it might need a single digit to represent them, or it might need a negative sign and then 3 digits to represent them. And how do you sort them? Can you just give me an idea of how you sort things? So maybe imagine yourself in a situation where you're sorting books, a stack of 1000 books, or maybe 100 books, and you want to sort them in ascending or lexicographic order of the titles. So word titles with A and then come first, and then B, C, D, and then within A, then you see the second one. So how do you sort this? What do you do to sort? So what is your idea? So think of the input as some list, and you're allowed to access elements of the list by inputting I in it. So I have sort, and my input is some list L. So how do I sort? Just intuitively, what do you do to sort? If you just look at numbers and you have to arrange them, what do you do?
Like find the largest one and
Yes.
then put it at the end.
Yes, just find the largest and put it at the end, and then among the remaining, find the second largest and put in the end, etc. Right. And so, yes, right. So let's do that, right? So first, okay. So this is sort of the last problem I'll write semi-formally. So, and okay, let's also assume that n is given to us, which is the size of the list. And so what do I do? And so, by the way, I'll use this to refer to as first element, the second element, third element, etc. This is the last element. So L of I would be the number that's at the ith position. So for j equal to 1, to n. I want to find the largest element, right? So let's keep a track of let's keep track of the largest element. Uh, large is equal to, for now, let's say it's L of 1 because that's all I have seen so far. And then from k equal to 2 to n, we update the largest element to, to max of whatever this element is right now and the largest that I've seen so far, right? Basically, what I'm doing is I keep track of the largest element that I've seen so far. So right now I've seen 4. Then I go to 3 and compare 3 and 4. And the max of those will be the new largest element. And then I go to 8. And then the max of 4 and 8, which is 8, would be the new largest element, etc. Right? But I also want to keep track of where I had seen this largest element. I don't want to go back and see, oh, okay, 17 is the largest element, but where was it? I need to keep track of that also. So I'll keep track of that by sort of with another element. So let me just remove it. So where largest is 1, because that's the position where I'd seen the largest element. So basically I'm storing the index of the largest element here and the largest element itself in here. So now if this number is more than the largest element, then my largest element becomes this element. And now where large, that is where is the largest element seen, becomes k, right? So all I'm doing is I'm going through the numbers one by one. And if I see a number that is larger than the largest so far, I'm updating the largest element as well as its location. This just tracks where it is on the this list, right? And after I've done this, so now let's say I know that large is 17 at the end of everything, end of all this. And I know that this where large is 4. So I have this information, right? So since I have this information, what I do is I bring this here and bring this here, right? So I sort of swap those elements. And swapping is easy, right? Just swap L of where large, or rather swap where large with the last index. Right? That's all. I just swap these elements and then I just sort the remaining things. So, and then I just sort the list with just the first n minus 1 element. And so once I reach 0, I should just say that just stop. Right? So I'll explain what I'm doing here. Stop. So what happens? So if I have, let's say, just this 17 and minus 2, then first I'll call sort of this. Let me call this list L sort of L and 5, right? Because there are 5 elements. And so now for this whole procedure, we'll find the largest element and where it is for me, right? So that will give me this. And then I'll swap these two and make it minus 2 and 17. And then after doing all that, I will now call sort of L and 4. And now what does that do? It sorts these elements. And then again, this is the largest, so this will swap these two, etc. Right then, so then this will become 8 and minus 2, and then this becomes minus 2 and 4. This becomes, well, this doesn't do any swapping, and then yeah, that's it. Right. So basically, I'll end up with the sorted element. I'll end up with the list being sorted. And how much time does this take? So you can show that the number of steps that this takes is some constant times the square of the input. this is still polynomial. It's the square of the input size as opposed to linear before. But that's also polynomial, right? So I have this set of problems, this class of problems called P, containing all problems that can be solved in polynomial time. And these are sort of called, well, just informally referred to as easy problems. Because polynomial time is just viewed as easy. Well, it may not be true practically, but well, theoretically we just refer to it as easy. Okay. So part one of this problem is done. So we now know what P is. It's the set of all problems. So note that this itself is not a problem. It is a class that contains problems. For example, the GCD problem is an element of P. And so is sorting, for example, and many other problems. For example, finding the largest element in a set. There are many problems which are not easy to show in P, but we've managed to show it. One such problem is this: given a natural number n, is it prime? You just need to output 1 or 0, depending on whether it is prime or not. And you might think, wait, don't we know a polynomial time algorithm for this? I mean, we know how to check if a number is prime or not, right? We check all divisors from 2 to square root of n, right? And so doesn't that take the square root of n time? But so this algorithm, so check from d equal to 2 to floor of root n, whether d divides n. I mean, if at any point there's yes, then you say that n is not prime, otherwise n is prime. But so then we have this algorithm. So then why is this? I mean, why did I say that it's not easy to show that it's here? Well, notice that the number of steps taken by this is like root n times some constant. But what is my input size? My input size is not n, it's the number of digits in n, right? So, but my input is actually just the number of digits in n, which is actually log n. So the square root of n is not polynomial in log n. It's polynomial, it's actually exponential in log n. So yeah, I mean, yeah, sure, exponential. So this is actually c times root of 2 raised to log or 10 raised to log n, depending on what the base is here. So this is not polynomial because this is the input. Yeah. So yeah, so this result is not trivial actually. That to test whether a number is prime or not is in polynomial time, and this was given in 2003 or 2. Not sure. I don't remember, but it was 3 Indian people who did this. So, and this test is called the AKS Primality test. Agarwal, Kayal, Saxena, all worked at IIT Kanpur. I think 2 of them were students of Saxena. And And initially, the complexity was something like log of n raised to 12 or something. This is ridiculous. You don't see these sort of expressions. But then it was later reduced to 9, and then if you assume the Riemann hypothesis, then you can say that the complexity is even smaller. So I mean, there are also conditional complexities on this. But yeah, well, it was just an incredible result, and this paper is actually something that you can understand by reading. So it's very cool. It uses polynomials and factorization of polynomials. So if you're really interested, you can give the paper a read. You can give it a try. Okay. Well, that's done. And now I want to talk about another class of problems. So let's start with this problem. Sudoku. So I assume everyone's familiar with Sudoku, but in case you're not, I'll tell you. It comes in newspapers often. It's a 9x9 grid. So it's like a 9x9 grid, further divided into 9 3x3 grids. And the goal is, and a lot of these numbers are filled up already using digits from 1 to 9. And the goal is to fill the remaining digits in such a way that each row, each column, and each of these 3x3 boxes has the numbers from 1 to 9 appearing exactly once. So just as an instance, suppose these are my rows. I'm just representing the first thing. Suppose I have a 1 here and a 1 here, and I have a 2 here and a 3 here. So then notice that since there's a 1 here in this row, a 1 here in this row, there can't be a 1 here or here. Well, actually, because there's a 1 in this box and there's a 1 in this box already. And so in this row, the 1 can only be here. So this is one of many strategies applied to solve a Sudoku. So, well, sometimes it doesn't work. If the Sudoku is harder, then you need to think of more complex tricks to solve it. Yeah, okay. I don't want to get into the details of Sudoku itself. But now, so classic, so sort of we know that Sudoku is in some sense harder than sorting, right? In the sense that for sorting, you know exactly what to do. But in Sudoku, sometimes you just try different things and hope it works out. Right? So here's what I'm getting at. So Sudoku, well, sure, 3x3 is not that bad, but you can think of a generalized Sudoku, which is n square cross n square, right? But just generalizing 9 to the square of n for any n, right? And think about this generalized Sudoku. And now think of this problem. Given an input, given an incomplete Sudoku instance S, is it solvable? Or you can even ask uniquely solvable. Let's just say solvable. It's solvable. And now if I ask you for an algorithm, it's suddenly not clear, right? How do you even come up with an algorithm for this? Sure, you can write down things like this, what I mentioned. If there's a 1 of such a pattern and 1 of such a pattern, then there should be a 1 here. Sure, you can code up these things. You can write up these things, and then there can be even more complex patterns. So for example, if everything here is filled up with numbers other than 1, then note that since there's a 1 here, then there must be a 1 here, because where else will 1 go? But the problem is that none of them are actually real algorithms, right? One algorithm that you can come up with is just to try every configuration of Sudoku and check if it's consistent, right? So that is one algorithm. So only complete algorithm that I can think of is go through every way of filling up S. Basically, whatever's incomplete, you just try every possibility of 1 through 9 and then check if it's consistent. And check consistency. Check if it works. Well, checking is easy, right? This part is easy. I mean, if suppose I've completed a Sudoku and I tell you, well, is this a correct solution? It's easy to check that, right? All you need to check is if each row and each column and each of these boxes has the numbers from 1 to n square appearing exactly once, and that's not hard to do. So this part is easy. The problem is this part. How many ways are there of filling up an incomplete Sudoku? Usually exponential, right? So exponential. Many ways of doing this. Needless, well, anyway, checking it is easy, right? So I want to emphasize on this, that it's easy to check it. But now take another game, for example, let's say chess. And maybe we could come up with some sort of a general N-cross and generalized chess of some kind. But in your mind, you can think of just a 3x3 board. But just keep in mind that there can be sort of generalizations of chess. And now suppose given a configuration, so there's a given a position and a move. Basically, I have a position and I make a move and I ask you, is it the best move? Or rather, given a position, does white win or something like that? So many different questions that can be posed with optimal play from both sides. That's something I assume. And now it's not even obvious what to do here, right? So, well, can you think of something that can resolve this problem? Like something which is sort of like brute force? You could try every possible move on every step and sort of branch out. That is one possibility. But now the number of steps is not just exponential, it is even more. Well, I guess yeah, okay. So maybe let's think about the previous one. Is this move the best? So how do you approach such a problem? Just think about it in this manner. Can you come up with something like this for the problem?
Well, we can brute force all possibilities, right? Like
Yeah, and how long does that take? Yeah,
probably even more than exponential.
right, you're right. And
Isn't it exponential because say you have 16 pieces and n square possibilities where they can go? So you have at most like 16 n square possible moves. So 16 n square to the power the number of moves the game can last.
Well, let's just say the 50 move rule is not applicable. Let's for this problem say
Then
that.
the game can never end.
Well, I mean, sure, but that doesn't mean that we can't answer this. I mean, well, that it's not true that the game can never end. It's still possible for it to end, right? Even if 50 moves rule is. Well, okay, sure. Let's just say that 50 move rule is true, but if you reach a configuration that
Oh yeah,
So-
if you remove the 50 move rule but keep it, this repeats 3 times, then
I guess something okay, sure. So
yeah.
okay, let's just ignore that. So sorry, what was your argument for the number of
So each move you have at most 16 n square possible moves because 16 pieces and each piece can move to like at most one of n squared cells. So
Yeah.
16 n squared possible moves for white or black.
sure.
So after say k turns 16 n
Well,
squared.
I mean, it's not 16, then the size of the board also increases.
No, 16 is the number of pieces.
Well, the number of pieces also increases. Let's say there are 2 n pieces on both sides.
Still, it's a polynomial, so 2n cubed to the k, which is exponential in
What is k?
the number of turns. So 2n cubed to the power k
But
is the
but
number
what
of
is k in terms of n?
Oh, right. So given an n into n general board, you must have some constancy of n, but that is not necessary. Yeah.
Yeah, the problem is that basically you're trying to count the number of different configurations of the chessboard, right?
Yeah.
Yeah, but how many configurations are there? So think about that. Each piece
So,
can be put in
like-
like n square places, right?
Yeah, n squared to the power n squared.
Let's say n square to the power 4n is also fine. Because there are just 4n pieces.
Yeah.
2n on both sides. So it's n square raised to 4n. That's the number of configurations. Sure. So okay, if that's the number of configurations, how much will you have to prove for?
Oh, you see.
The point is it exponential? It might be exponential. Yeah, actually it is probably exponential. You're right. Because if there are at most, well, if there are 2n pieces and then each piece can be put in at most n square squares on both sides, then there are at most n square raised to 4n configurations times some constant, depending on whether castling is allowed or whose turn it is. It's not just the position, but it also matters whose turn it is and what flags are checked. So those are counted as different configurations. So no matter what, it will be some overall. This thing will be an exponential function, right? This is exponential, and now if we apply the threefold repetition rule, we cannot enter a configuration more than 3 times, right? 3 or more times. So it is exponential in n. But where is this aspect of checking here? Is there any aspect of checking in this problem as we had in the Sudoku puzzle? So what I mean to say is, if I tell you the best, so here if I tell you the solution, then it's easy to check whether that works or not. So that is, if there is some divine intervention and you've given the solution to the Sudoku, then you can verify that it is correct. But here, if I give you the best move, can you verify if it's correct easily?
No, it's equally hard.
Yeah, almost equally hard, because after moving the best move, you now need to analyze this compared to every other move and check whether this is indeed the best or not. So it's not like giving the solution doesn't make it easier. So sure, easier. right? So here's what I'm getting at. There's a class of problems. So actually, let me take another example. So if you're familiar with okay, sure. So I have a graph G. It's a simple graph G. If you don't know what a graph is, it's just like a collection of finite points, and then there are like lines joining any two. So there may or may not be a line between them. There's only at most one line between any two, etc. So my task is to hold on. So the question is there a is there a way to start at a point or a vertex and go through each vertex exactly once by traveling along the edges? Traveling along the edges. And immediately coming, let's just say this. So for example, here the answer is yes. I can start from here and go here, then here, 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 and here. But then there are other graphs where it may not be there. So again, the task of finding an algorithm which is polynomial time is something that we still don't know how to do. So is this problem in P? We don't know. I mean, does this problem belong to P? We do not know. However, again, if someone just suddenly highlights this part for you, well, but if someone tells you the part, so basically, if someone tells you a hint, quote unquote, in which in this case is the part itself, then it's easy to now answer the question, right? Well, okay. Well, it's easy to answer the question in the case that the answer is yes. So okay. So if there is a path, if there is indeed a path in this, and someone gives you the path, then it's easy to check if that is indeed a path, right? So what I mean to say is, if G has such a path, this path is called a Hamiltonian path, by the way. Such a Hamiltonian, just Hamilton sometimes. But then if some third party tells you this path, then it's easy for you to be convinced of it. Then you are convinced of it, that there is such a path. That there is such a path. Similar thing happens in the Sudoku puzzle, right?
Like here, you can probably just say by O's theorem, you can somehow count it like by taking.
Well, I mean, in the Sudoku puzzle, you just need the solution, right? And the Sudoku, so if it is solvable, then the third party can just tell you the solution. For example, just at the back of the newspaper, you can look at the solution and be convinced by checking it yourself that indeed this is correct. So the point is there is a class of problems P such that if okay, so this class of problems is special in the sense that the answers are either yes or no. So we only look at questions that have yes or no answers. So containing yes no problems. For example, this was a yes no problem, right? Can we, is there a way? So I asked, is there a way? Here, is it the best move or is it solvable? While some problems here that we looked at are not actually yes no problems. So sorting is not a yes no problem because you need to output the entire array. But I could convert, I could ask, if is this list sorted? That would be a yes no problem. Or I could ask, is this number the largest element in the list? So that's a yes no problem. Or I could give you three numbers A, B, and G and ask you, is G the GCD of A and B? So that's a yes no problem. So we only consider yes or no problems containing yes or no problems. These are also called decision problems because you need to decide if it's one or the other. Such that if we get a yes instance, again, keep in mind this previous example. If I get a graph that has such a path, then a third party can easily convince me of the answer. That is, my task of actually proving that this is yes is made much easier by this third party. So let me give you one more example. So here, here another example. I have just thinking of something not too complicated. Okay, yeah, I have a set S of elements of numbers, that is. Is there a non-empty subset such that the sum of the elements in T is 0? T is 0. Again, if the answer is yes, then a third party can easily convince me of it by providing the set itself, right? So this is satisfying. So just look at this and see if you can fit the Sudoku problem and this Hamiltonian path problem into this definition. So all of them are actually instances of are in this class of problems. Because whenever the answer is yes, it's very easy to convince. So think of me as a doubter who doubts that there is such a set. But then if there's someone else who gives me the set, then I'm convinced of it because it's very easy to check instead of just going through all exponential possibilities. This is a very easy task to do. So by convince me of it,
Is
it-
easy to verify equivalent to having a polynomial time?
yes, that's what I was getting at. You're
Okay.
right. So when I say convince me of it easily, I mean easily. By that, what do I mean? I mean that I will have to put very little effort. I will need to put only polynomial time effort. So here, that is in another way, I want to frame it in a different way. If the answer is yes, then a third party can give me a clue. Well, okay. then can give me a well, okay, let's clue that such that I only need polynomial time to such that I only need polynomial time to agree with the yes. On contrast, by the way, suppose the answer to this was no. That is, suppose this did not have a Hamiltonian part, then now it's not easy how a third party can actually convince me that the answer is indeed no. Because, or at least we don't know of such a way to convince. So, but consider this problem. For example, given A, B, and G, is G the GC? So let me write this down. So what about this problem? Given A, B, G, is G equal to GCD AB? Here the point is, I don't even care about this third party. I can anyway do it in polynomial time and figure out the answer, right? So this is also a part of this. So even if the answer is no, I can still do it in polynomial time. So, and if the answer is yes, even then I can do it in polynomial time. So the point is all polynomial time problems belong to this class because I don't even need the third party. I can myself find the answer. But now this, by the way, this class is what is called NP. So the point that P is a subset of NP is true because again, I'm only taking yes or no problems in P. So just discard the problems that are not yes/no. So the point is that if I take a problem here, then it also belongs here because this is true sort of vacuously because I can just be convinced by myself. So I don't even need this thing or a third party. So P is a subset of NP. Now the problem is we don't know if NP is a subset of P. So this is the open problem. Is P equal to NP? And let me give you reasons. Let me give you one reason why most people believe that NP is not equal to P. Let's get into that discussion for a while. So first of all, notice that P basically talks about problems that are polytime solvable. That is, we can spend polynomial time and actually solve the problem and decide yes or no. While, so I only need polynomial time to decide whether the answer is yes or no. While what does NP do? NP says that if the answer is yes, then it's easy to verify it in polynomial time. Fortunately, if the answer is no, then NP does not exactly help them, right? So does not say anything about this. So it seems so particular that NP only talks about problems that are verifiable in polynomial time, while P talks about problems that are completely solvable in polynomial time. And it just seems so incorrect that you can solve a problem in polynomial time. And I mean, if you can check a problem in polynomial time, then it's also solvable in polynomial time. So think about this. So this is a rough idea. So think about proving a theorem. So you have some sort of a theorem. There's a formal definition of what a theorem is. It's a bit different, but let's just go with it. So suppose I have a theorem. Now, if I have a proof of this, proof by definition has polynomial length actually implicitly. then it's easy to check the proof. So actually, there's a formal definition for proof. A proof is like a statement of logical steps. So it's like P1, P2, such that each PI is implied by the previous ones and through axioms. Right. So that's what we do, right? So we write something which may be an axiom, and then we use that to maybe get P2, and maybe P1 and P2, and some other axiom like P3, etc., till we get to the last step of the proof, which actually proves the theorem. Right? And so now checking each of these steps is actually easy. So if there is a proof, then checking a proof is easy. But if P were equal to NP, what does this mean? It means that you can also prove the theorem in polynomial time. So, but if P were equal to NP, this means we can also prove the theorem in polynomial time. And why is that weird? It's weird because then we're saying that for any theorem, if it's easy for us to read the proof, then it's sort of easy for us to also come up with the proof in some sense. And then no matter how complicated proofs are, so think of a theorem that has some proof, and a computer can go through the proof and actually know whether this proof is correct or not. And so that means that if P were equal to NP, then the computer could also come up with a proof in polynomial time. And so we don't even need mathematicians. I mean, everything can be done by computers. So that's one logic. That's one. But everything I said is very vague. But the idea is that if we can understand theorems, we can also, or rather, understanding theorems is as hard as proving theorems, which seems sort of wrong, right? Because we just by experience, we know that it's much harder to prove a problem or solve an Olympiad problem than it is to just understand or read through the proof of it. So that's one reason why people think that P is not equal to it. I mean, this is not the reason. There are many other reasons why people think P is not equal to NP. Of course, there are people who also believe P is equal to NP. I mean, there's a lot of division among this. There are also people who think other things. So there are people who think that P is equal to NP cannot be resolved under certain axioms. So it's sort of independent of axioms, but whatever. So yeah, so in summary, well, P is polytime. NP is well, polytime verifiable. We know that this is a subset. In fact, if we go to the class of problems that are exponential time solvable, then we know that this is actually a subset of this. Yeah, we know this. So actually people use like circles to represent this. So let this be X. Then actually let this be NP. Then this is, sorry, this is outside, it should be inside. This is P. Well, it might be the entire circle if P is equal to NP, but we don't know that. And then there are other problems. There are many problems which are inside P as well. So there is something called space complexity. So what we mean by space complexity is how much rough space is needed for you to solve it. So like a computer has memory, right? So if you give it a problem to solve, how much of its memory is it using in terms of the input size? So that's space complexity. And so we know that if a problem can be done in at most S of n space, where n is the input size, then it can be done in 2 raised to S of n time. So we know this. So we know that. So if I have log space, then that will be inside polynomial, because 2 raised to log is polynomial. And then P is itself contained in something called P space, which is polynomial space. So we also know that that T of n time problems can also be solved in T of n space. So we know this, and this in turn from here is 2 raised to T of n time. And so we know that X lies somewhere outside. This is X. We write it on the line, so it's clear. And then there's another class of problem called polynomial space, which is here. So we know these sort of inclusions. L is in P, is in NP, is in P space, is in X. There are many other things that there are problems that ask you, well, if the answer is yes, then output yes with probability at least 0.9, and if no, then answer no with probability at least 0.9. So those are called bounded polynomial time, probabilistic polynomial time problems, and then that is sort of like this. This is bounded. I mean, it's like a whole zoo of complexity classes. There's a complexity zoo. And the surprising thing is that we don't know any of these is strict or not. The best here we know is that P is not equal to X. So we know that P is strictly contained in X. And so we know that either this is strict or this is strict or this is strict. We don't know which one. So then we have even more generalizations like NX and then EEX, then EENX, etc. And then we have this hierarchy, and then the end of it there's something, and then well, then there are sort of branches to it. Just all this sort of stuff, which is
How was P disjoint subset of X proved?
well, there is something called time hierarchy theorem, which I mean, if I had time, I could have done it. I mean, it's all part of like a standard complexity course. But what time hierarchy theorem states is that, well, roughly it states that if a function is the square of another, then there exists the problem P that can be solved in f of n time, but cannot be solved in g of n time. So that definitely proves this, because exponential is definitely, I mean, it's much more than the square of one. And so yeah, so this is time hierarchy theorem. Then we also have things like space hierarchy theorem, which is something similar to this. And yeah, I mean, yeah, this is the main method to prove that P and X are separated from each other. So more precisely, we can also say if f of n is much more than g of n log g of n. But the square thing is true. So this is more precise than, for example, if g of n is n, and if I take f of n to be n times log square n, then this is true. Just anything which is much, maybe this is better to write. So if I have functions f and g such that f of n upon g of n log g of n tends to infinity, then this is. So yeah, this is the main method to prove that this is separated. But we don't have much more separations. Can also separate this. And then there are conditional results as well. We know that if x is equal to nx, then p is equal to np. We have these sort of results. So yeah, so we have conditional results, but we don't really have results that are quite independent. So a lot of these results are conditional, and there's a lot to prove in complexity theory. Lot of it is open. We just don't have the techniques to prove these things because mainly we're good at solving problems. We're good at finding algorithms. So just historically and just in general, it's true that we're good at finding algorithms like these, like finding A1, then finding the way to sort and harder problems. We just don't have the techniques to prove lower bounds like these. Yeah. In fact, even in complexity theory, there are a lot of results that rely on algorithms. This time hierarchy theorem is proved using a particular sort of algorithm. So the idea is to find sort of like a pathological algorithm that that satisfies this. So yeah, we're good at algorithms, but not good at finding lower bounds. So yeah, just we really lack techniques mainly. So that's the issue. Yeah, that ends my talk. So if you have questions, please ask. Oh, by the way, there is this website of complexity zoo. Let me just find it. Like, if you Google complexity zoo, you should come up with it. Yeah, complexitysoo.net. It's like constantly being updated. I think I don't know if it's updated now, but yeah, the zoo was open. It's sort of like a Wikipedia page for complexity classes. It was opened in 2002 and made into a Wikipedia in 2005, and then yeah, you can just go through it and see if something interests you. Just look at the number of different complexity classes. I don't think I know even 5% of these, not even that much. It's just too vast. Everything is very interesting. There are, in fact, there are complexity classes related to games as well. So there's some sort of a class called pigeonhole problem. I don't remember what it's called. I think it's called PPP. Pigeonhole something. So I think that's. Okay, let me just find it now. Polynomial pigeonhole principle. That's the name of the problem. So it's all fun. Just check it out if you want to. Questions?
How long do you think will this problem take to solve us?
That's a good question. I still think it's just we lack so much technique to even prove basic results now. That we can't even prove that. Okay, so there's this problem called the three-sum problem, which is given three numbers. Given a set and then a target, can you find three numbers that sums to the target? So we don't even know. Well, we know algorithms that are sort of close to quadratic time, but we don't even know if we can't prove that there is a quadratic time. There is an algorithm which is faster than quadratic time, or that there is no algorithm faster than quadratic time. So we can't even prove these sort of polynomial related problems. And well, I mean, I'm not saying that this problem should be easier than P versus NP. In fact, probably not. But the idea is that we just don't know much about lower bounds, that it's very hard to say how much time it will take to solve the P versus NP. Maybe, I don't know. It could be as much as like 50 or 60 years, or even more. And it could be 200 years, who knows? Or maybe doesn't get resolved for a long, long time. Yeah. Whatever development there has been in complexity theory, none of it has been very directed towards solving P versus NP, except for this very particular project on something called geometric complexity theory, which was started by it's started by two Indians, Ketan Mulvule and William Sohani. So this is one main program started in, I think, 2000 or something, which specifically wanted to discuss complexity theory to prove P versus NP. And they go into this geometric complexity theory. It's all interesting stuff, but I mean, even there has not been much progress over the last 20 years. And that's not the first time geometric complexity theory occurred. I mean, was started. I mean, it existed even before that. So there's been a lot of there's actually not been a lot of directed effort towards proving P is equal to NP. So I guess if you want to get it resolved fast, I think a lot more people might have to work towards it, or yeah. I think the main thing is just lack of technique. I think that's the thing to emphasize on. We just have just a dirt. You just don't have techniques. Yeah. So yeah, I don't know how much time it will take to solve it, but definitely probably not in the if I had to take a guess, probably not in this century. Other questions? Well, okay, yeah. The Wikipedia page itself says that if this program is viable, it's likely to take about 100 years before it can settle the P versus NP problem. I mean, definitely, I believe that it'll be probably much more than 100 years. Okay, I guess we can stop the session now.